Thanks for dropping by during my office hours. Today, we will discuss some important fluid properties. 1. Density. Density, in practical terms, refers to the mass of a substance per unit volume. Water density is a crucial measurement, typically hovering around 1 gram per milliliter. However, this value fluctuates based on temperature and dissolved substances. Notably, ice is less dense than liquid water, which explains why ice cubes float in a glass. Interestingly, water reaches its maximum density at 4 degrees Celsius. In the structure of ice, water molecules arrange themselves in a crystalline pattern, creating considerable empty spaces. At 4 degrees Celsius, clusters start to form, causing molecules to move apart despite slowing down. This cluster formation becomes the predominant factor, leading to a decrease in density below 4 degrees Celsius. As the temperature rises above 4 degrees Celsius, water molecules speed up in distance from each other, resulting in decreased density. 2. Specific weight. The specific weight, also known as the unit weight, symbolized using the Greek letter gamma, is a volume-specific quantity defined as the weight per unit volume of a fluid. Like density, it can be used as a characteristic property. Let's recall that weight equals to the product of mass m and gravitational acceleration g. Then, let's substitute the weight equation into the equation of the specific weight. Now let's recall the definition of density, that density is the mass per unit volume. It won't be too difficult to realize that specific weight can be linked to density as shown here. Unlike density, specific weight is not a fixed property of a fluid. It depends on the value of the gravitational acceleration, which varies with location. Pressure may also affect values, depending upon the bulk modulus of the fluid, but generally, at moderate pressures, has a less significant effect than the other factors. For water, a commonly used value of specific weight on Earth is its value at 4 degrees Celsius, which is 9.808 kilonewtons per cubic meter or 62.43 pounds force per cubic foot. This is because the density of water at this temperature is 999.84 kilograms per cubic meter. Additionally, the standard gravity is acceleration due to gravity, usually given in meter per square second, and on Earth usually taken as 9.81 meters per square second. 3. Specific gravity. Specific gravity, ratio of the density of a substance to that of a standard substance. Because it is the ratio of two quantities that have the same dimensions, that is, mass per unit volume, specific gravity has no dimension. The usual standard of comparison for solids and liquids is water at 4 degrees Celsius or 39.2 degrees Fahrenheit, which has a density of 1 kilogram per liter or 62.4 pounds per cubic foot. Gases are commonly compared with dry air, which has a density of 1.29 grams per liter under so-called standard conditions with a temperature of 0 degrees Celsius and a pressure of 1 standard atmosphere. For example, liquid mercury has a density of 13.6 kilograms per liter, therefore, its specific gravity is 13.6. The gas carbon dioxide, which has a density of 1.976 grams per liter under standard conditions, has a specific gravity of 1.53, calculated using 1.976 divided by 1.29. Because specific weight is the product of density and gravitational acceleration, specific gravity can also be defined as the ratio of the specific weight of a substance to that of a standard substance. For solids and liquids, this standard substance is water at 4 degrees Celsius, with a value of 9.807 kilonewtons per cubic meter or 62.43 pounds force per cubic foot. 4. Viscosity. Viscosity is the resistance of a fluid, be it liquid or gas, to undergo a change in shape or to allow the movement of adjacent portions relative to each other. It signifies the inherent opposition to flow within the fluid. The reciprocal of viscosity is termed fluidity, representing a quantitative measure of the fluid's ease of flow. Molasses, for example, has a greater viscosity than water. Because part of a fluid that is forced to move carries along to some extent adjacent parts, Viscosity may be thought of as internal friction between the molecules. Such friction opposes the development of velocity differences within a fluid. Viscosity is a major factor in determining the forces that must be overcome when fluids are used in lubrication and transported in pipelines. It controls the liquid flow in such processes as spraying, injection molding, and surface coating. In numerous fluids, the tangential or shearing stress, which induces flow, exhibits a direct proportionality to the rate of shear strain or the rate of deformation incurred. In simpler terms, the ratio of shear stress to the rate of shear strain remains constant for a specific fluid at a consistent temperature. This unchanging ratio is referred to as dynamic or absolute viscosity, commonly known as viscosity. Fluids exhibiting this behavior are categorized as Newtonian fluids, a nomenclature paying homage to Sir Isaac Newton, the pioneer of this mathematical depiction of viscosity. The viscosity of liquids decreases rapidly with an increase in temperature, and the viscosity of gases increases with an increase in temperature. Thus, upon heating, liquids flow more easily, whereas gases flow more sluggishly. In certain engineering applications, kinematic viscosity proves more practical than dynamic viscosity. Kinematic viscosity is the dynamic viscosity of a fluid divided by its mass density. Its dimensions are expressed as area divided by time, with the appropriate units being square meters per second. 5. Vapor pressure. Vapor pressure, also known as equilibrium vapor pressure, refers to the pressure exerted by a vapor in thermodynamic equilibrium with its condensed phases, whether solid or liquid, within a closed system at a specific temperature. This equilibrium vapor pressure serves as an indicator of a liquid's inherent thermodynamic inclination toward evaporation. It signifies the equilibrium between particles escaping from the liquid or solid phase and those existing in a coexisting vapor phase. A substance characterized by high vapor pressure at standard temperatures is commonly termed volatile. Vapor pressure is the measure of pressure exerted by vapor over a liquid surface. With an elevation in liquid temperature, the dominance of attractive interactions between liquid molecules diminishes compared to the entropy of those molecules in the gas phase, consequently raising the vapor pressure. Therefore, liquids featuring robust intermolecular interactions are prone to exhibit lower vapor pressures, whereas the converse holds true for weaker interactions. The vapor pressure of a liquid influences the pressure exerted on it by the atmosphere, leading liquids with high vapor pressures to exhibit lower boiling points. By heating a liquid, the vapor pressure can be elevated, allowing more molecules to enter the atmosphere. Boiling initiates when the vapor pressure equals atmospheric pressure. In the absence of external pressure, liquid molecules can disperse, transitioning from a liquid to a gaseous phase. The resultant gas, forming bubbles within the liquid, ascends to the surface and is released into the atmosphere. In water supply and distribution systems, insufficient transient pressures can lead to the vaporization of liquids. Subsequently, when one or more of these vapor pockets collapse, it can generate substantial transient pressures, potentially causing damage to pipes or other components within the system. Thank you for tuning into this video. If you have any questions or specific civil engineering topics you'd like me to cover in future videos, feel free to leave a comment below. Your likes and subscriptions motivate me to create more content, ensuring you don't miss out on future updates.